So my name is Etienne Caron. I'm a software developer from Montreal, Canada. I run a small consultancy called Canastruc, where we specialize in Kotlin development. Now, before I get really started, I want to give huge thanks to the DroidCon organizing team. It's an awesome event. They've been really nice, and I'm really grateful for the opportunity to present to everyone here today. I also want to give a big thanks to Google. Now, they've helped sponsor my travel here since I'm part of their great Google Developer Expert program, so big shout out to them. They've always been very supportive, and as lockdowns have ended and the community's booting back up, they've been a great help. So, if you haven't had the chance to grab one yet, or you probably have one now, I have these little notebooks. If you're coming in late, you can grab one later. The bag is right here. I'd be happy to give one to you. These were designed by my wife, so I want to say thanks to her as well. If you open them up landscape mode up front, you're going to get a few key slides in the presentation. You can take notes if you have a pen. I didn't bring pens, I'm sorry. And on the other side, in portrait mode, you're going to get a nice little grid paper to doodle with, as you can see here. All right, so let's get started. Now, with the modern application, when you want to build something out, you need to target iOS, Android, and web because they're table stakes now, right? So that can be really challenging if, like me, you're a very small team of one, and you're trying to build out projects and get customers with very limited dev resources. So Kotlin Multiplatform is a very promising solution for that. It allows you to basically target mobile platforms for sure, but also the web. And that might be one of the key points I'm going to talk a little bit about today, even if I'm not digging in too much into it. Targeting the web, I find, is often neglected by us mobile developers, and having a chance to do that is really powerful. And so I can punch above my weight effectively. That's the approach I picked with my company. All right, so today I'm going to share with you the learnings I've had so far working on KMP projects. So one of the big strengths of Kotlin Multiplatform is that it allows you to write native applications. So apps built with KMP are able to use the latest and greatest APIs for your target platform. Now, as you've probably heard before, that's the big difference between other cross-platform frameworks like React-Native and Flutter, because they effectively end up having to run after the host platform. So that's the small downside into using those. Obviously, though, there's also a little downside with Kotlin Multiplatform. If you're going to write code that targets native platforms, that code will become single-use. So even if it is written in Kotlin. To stay efficient, you need to put your efforts where it counts. So I came up with this little code reusability table to guide my own efforts. Now, common Kotlin code is effectively your best payoff. If you can put most of your code in there, you're going to use it everywhere. It's wonderful. Android is a bit different. It's where you can dig for gold if you're actually converting an existing project that you have in your Android ecosystem, and you want to bring it over to multi-platform. I've done this a few times, and I found that I could reuse most of my business logic, both on the web and on iOS. Now, if you move over to iOS, your UI code is going to be Swift or Objective-C, God forbid. So that's single use. Effectively, you won't really be able to reuse it. The silver lining there is that you can consider Mac on desktop as a target as well. And we end up with the web. When you write your web client with Kotlin.js, your code is technically reusable. So that's similar to Android. You can dig for gold a little bit in there. In my experience, though, what I ended up with is often, it's not a very polite term, I'm going to say polluted code. What I mean by that is when you write Kotlin.js, it is pure Kotlin, but you do have access to certain JavaScript-specific things and the APIs. And it sort of tends to flavor everything. So I've found that it's a bit like Swift UI and that you're writing UI code that's not entirely reusable outside of the web world. No, that mental chart was useful to me, but I think the right architecture and good dependency injection is really what has the biggest impact code reuse-wise, and that's really what we're going to start digging into now. So my architecture of choice, as you probably guessed from the title of the talk, is MVI. Now, I find it helps me reuse code, and it also helped me focus on the right problems at the right time. So to get started on the right foot, we're going to have a small MVI overview that I'm going to go through with you now. One thing I'd like to say, though, is that MVI, in my opinion, is more about adopting big principles than enforcing rigorous frameworks. I've seen MVI approaches that are very process-heavy, so that's not what I'm going to be showing you today. There's 4 big principles I try to keep in mind when I'm developing an application. Now, the first one is unidirectional data flow. There's immutable state, functional programming principles, reactive programming principles, and so now we're going to start with unidirectional data flow. Now, it's a deceptively simple concept. With MVI, in this case, we'll have user interactions that are coming in from the view. Those get converted to intents that are processed by the model. Then the model will update its internal state, and with that, the views that are subscribed to the model will update themselves accordingly. Now, unidirectional flow is not magic, but when you use it correctly, it allows you to modularize things in potentially crazy ways. Now, I'm not saying that this is necessarily good architecture, but what the slide here is trying to express is that regardless of what model components you have, you can assemble them in ways that make sense to your app. Another critical principle of MVI is that models use an immutable state. Now, we rely on data classes since they enforce immutability. The big benefit of using data classes is that view code that would be trying to mutate a model simply can't compile. Now, this is great, right? If direct state mutations were allowed from the view code, other views wouldn't find out and wouldn't refresh, instant bug. Immutability is important, so without it, what happens is that you risk ending up with shared mutable state. So whenever you have a state which is data persisted over time, that can be modified, and where concurrent access is possible, you have shared mutable state. Now, avoiding shared mutable state is one of the core functional programming principles. It's effectively the root of all evil in development, a close cousin to global variables. Functional programming principles also promote the use of pure functions. Now, pure functions always return the same value for a given set of arguments, and they have no side effects or side causes. So that means that they can't mutate the value of a variable, they can't read from disk somewhere, and so on and so forth. Now, of course, most applications will eventually need to store state and interact with the outside world, right? And this is why MVI architecture only really borrows from functional programming and is not a pure functional approach. So that said, MVI implementations do use various strategies to isolate side effect heavy code from more functional code. MVI also borrows from reactive programming principles. Now, reactive programming is all about creating streams of signals and subscribers that react to those signals. And as I've seen in the last day and a half or so, I think this is something that the community has recognized as a very common way of working things out, right? In MVI also, we are going to be creating components that expose streams of model state on the output side. On the input side, we typically will use handler type functions like this one. Now that stays true for the view, different implementations, but conceptually it's very similar. Now do note that this slide code is valid for JavaScript and Android and JVM based code. Obviously on Swift we're going to have to do things a bit more differently, but we'll touch onto that later. So that's the short intro to the big concepts of MVI. Now, our goal with MVI, in our case, is to create a very clear boundary between the aforementioned side effect heavy code and our more abstract business logic code. So this approach will help us reduce code complexity and allow ultimately for much better code reuse, which is the whole name of the game here. Now, context is king, and to frame today's discussion, I want you to imagine we're going to be building a small mobile app. And if you're like me, you're a bit bored of the to-do apps, right? That's what we see all over and over again. Instead, we're going to imagine a habit tracker app. So what we want here is a screen where we see our goals and we can track our progress. Each bar there will represent a habit. We'll track habit entries and we'll let users know that they're doing well relative to the different goals that they set for themselves, right? The top bar here will allow us to zoom into any given day of the week. The bottom bar is going to be a grab bag of funky features we're not obviously going to look into due to time and other constraints. So we're also going to need a screen where we create new habits or edit existing ones. So this editor screen in this here will have habits that are tracked weekly or daily. And based on their type, they'll represent a plain counter, something like counting your visits to the gym that week, or a one-time event, say like call your parents. Other things like tracking the amount of water you drink, what's your protein intake, so on and so forth. Okay, so how are we going to structure this project? So we're aiming to build a multi-platform project. We want to target Android, iOS, and the web. Now, workflow-wise, it's worth noting that if you're developing apps and your common block of code, common module, sorry, you could use Android Studio. That works fairly well. It is worth also saying that it depends on the version you're using and the weather that day. But myself, I found that a good experience with like the most current release of the actual stable Android Studio will work well. Then on iOS, you would obviously have Xcode open as well. I like to have app code also because as an Android dev and somebody that's really used to the JetBrains tooling, it helps me sort of get coding faster. And then on the web, IntelliJ is still a bit of a better citizen than Android Studio. So that's a bit of a downside. You're going to end up with most likely 3 different editors open at the same time. All right, so looking at the project configuration, the top-level Gradle build file is nothing special, super typical. The star of the show, so to speak, is the libcommon module. Here you need 3 different plugins. You're going to need the multi-platform plugins, the CocoaPods plugin, and the Android library plugin. Now to configure the Android plugin, if you're coming in from Android, again, nothing new here. It's much like any other library module. And now the Kotlin block is where the bulk of the configuration is going to live. Now, we start configuring the Kotlin Multiplatform plugin by adding all the platforms that we want to target. So here, did I add JVM? You could also target JVM desktop and things like that. You know, that's here. This is like your fairly typical setup. Then we want to configure the source sets for each of those targeted platforms. So each of the platforms has its own list of dependencies, as you can see here. But it's mostly important to understand, oh, there's a little bit missing in my slide, but it's important to understand that common dependencies are going to be carried over to the specific target platform. So whatever you put in the common main and common test here is going to be accessible by the other ones. Any other, obviously, platform-specific dependencies are going to be added in the right blocks. So to close off that specific Gradle file, the iOS CocoaPods configuration is one that's important to talk about. So if you're not familiar with CocoaPods, it's a dependency manager for Swift and Objective-C projects, much like Gradle and our way of pulling in dependencies from the different repos. As I mentioned earlier, the iOS app itself is an Xcode project. So by configuring the CocoaPods plugin in this way, we're going to make the Kotlin Common Code library available to the iOS build. And then behind that, there's a lot of magic that's going to generate the different files that the iOS side of things needs to tap into that. So how much code reuse can we expect from this project? Well, I've touched on it with my code reuse chart earlier. Well-written model code will typically all land into the common module. And then the views on the other end will all be very platform specific. If anything, though, that's a feature of the Kotlin multi-platform approach. So we're going to see exactly how much code we get to share between all of this. Now the model end of things will store habits state. Habits and entry data are bundled together into something called a habit state. In our app, where we keep an in-memory cache of the user's habits and entries, nothing super sophisticated, obviously. It's clear that basic data and state class types, they can comfortably live in the common module code. But how much of the actual logic can we expect to share here? So could we possibly make it mostly platform independent? So first we need to think about what interface our model will expose to the view, as right here. We use state flows to build the habit store. That's our model's output. And then having access to coroutines and flow in a common code module is really a big deal, as you can imagine. Stateflow allows us to publish our model state to views in a very safe and consistent way, and it's usable everywhere. So that's For me, it was almost a surprising thing when I saw that coroutine and flow were supported in common code, multi-platform-wise. I think that's like the critical big rock in the whole thing. On the input side, MVI models will typically expose one or more intent processing function. Now, the most basic version of this is the process intent function that we can see here. And depending on your MVI approach, though, you might want to create an intent builder layer. And this would be a dispatcher that converts view events into proper intents as objects, and then those you would pass on to your model's process function. Now, the thing is, in my own experience, I've found that it's often quite acceptable to expose a more prescriptive set of intents. So just straight up adding these process functions on the model and having them be your API. So that works if your app is slightly more simple like this one, and both approaches are valid. I think at the end of the day, it really depends on your code base and how to keep it the cleanest and keep things nicely separated. All right, so that said, when I'm building an MVI model, there is one thing I feel pretty strongly about as a must, and that's intent validation. Now, for example, to validate that an intent is good, I will usually build myself a state machine of some kind. So in this case, in this example, our model's cache state transitions are, I think, a pretty good example. So in model initialization, we're going to be loading the habit data from the server, straight up when we boot the model, so to speak, or we create it. Then whenever the user is going to be adding a habit or an entry, we're going to need to send over that new data to the backend server. When that's done, we take a naive optimistic cache type approach, and we're going to update the in-memory cache incrementally, flagging it as modified as we go. So then when we land in, say, a failed state, we can force a reload operation to go back to a clean state. So the idea, again, is that this little diagram, this little state machine, is going to enable us to enforce and check that when we call processing intents, we can't actually call one that would put us into effectively an illegal state. So to enforce it, the way this works is I would usually personally build a valid process function of some kind that was going to soft fail any intents that don't respect a certain predicate. So here, if the cache is not modified, failed, or loaded, I'm going to straight up ignore the call to reload intent. And also, error events flow can be useful if you want to notify your users of soft failures. So this here is not like a state flow, it's really a shared flow. So it's not something that keeps state, it's only really a broadcasting signal that if your view is there to listen to it, can react to it and show like some kind of error pop-up to your user or something like that. So, if you're not into soft failing, which I know some people are not, and I really get the idea, there's always the idea that you can throw simply an illegal state exception. It's a surefire way to catch problems very, very early, and then depending on how rigorous you are with your unit tests, that can definitely become a better approach than soft fails. If your unit tests are really comprehensive, so if something would trigger a problem, it'll pop right away. I personally prefer the soft fail net approach because you don't want to get called by your customers because your app is potentially you caught all those problems, but if you didn't and then it explodes in production, that's kind of sucky. And most errors in those cases can be you can recuperate the app state from it. All right, so, and in my experience, the second I need to get serious, wait, I skipped something here. All right, so, yeah. Small problem with my slides. There's always one of those slides in any given talk, isn't there? Where was I here? I think I literally lost a slide. Anyway, what I wanted to get into here is that, my whole point was basically saying you might not want to use these state machines, but I'm pretty adamant about them in my own project. Like the second, for example, that you need to get serious about user authentication and session management, you sort of end up in a state where you need something like that. I feel the effort pays off pretty much very quickly. So here, for example, when I end up with waiting states that impact what I want to show users on screen, like the second you have those asynchronous processes going on and you want to sort of adjust your UI to just tell the user, hey, give me a second here, we're processing, the state machines are quite useful. All right, another big, yeah. So here we're going to go on to another big cornerstone of your common code module, and that's the Ktor library. Now, Ktor allows you to do all your common REST API calls, like get, post, etc. It makes it really easy to define your REST calls as well. So you see this is a simple get definition right there. You also can use Kotlin serialization for marshalling and demarshalling your objects, so that's quite powerful and keeps things really tidy. And code-wise, I think it's comparable to using retrofit on Android. I won't lie, I prefer retrofit, but for now, it's not something you can use multi-platform. So Ktor is the good alternative, I feel. View framework-wise, well, Compose, our beloved declarative UI framework. High-level concept is that if you declare your views as functions, right, that these, the data that these functions consumes, and Compose will smartly rebuild different sections of your UI based on whatever changes are seen in the data. So here, for example, if the habit view functions take in a habit state and an event handler, the scaffolding here will let us configure the top bar, bottom bar, and the floating action button. The tail end function right there, it builds a lazy list from the habits state data that we're getting from the server. And so you can also see that there's an internal editing mode state right there. Now what that allows us to do, and that state is internal to the view, it's not exposed anywhere else, right? So it's an internal mutable Boolean, and it will remember savables for persistence across reconfigurations. So that editing mode internally is used to basically say, okay, we're going to flip and put up different affordances to the user so that they can, add an edit mode. Like, to be absolutely honest, this kind of UI is a bit horrible, but it's more there for the example of the idea that if you desire to have like a UI that knows how to flip itself on and off and toggle itself, and that it doesn't actually matter to the model that you're in the editing mode, all the model cares about is what the user will do, and that's one way to go about it. Now, one of my favorite things about Compose is how easy it is to attach a model to it. I'm just going to check how we're doing on time. I don't even know when let me see, 10:30, there's a break. Okay, we're good. So yeah, one of my favorite things here is that with habit store, we only need to call collect state and pass it on straight on to the habits view like this. Compose will trigger recomposition whenever a new state comes up with this. So not only that, but Compose has the APIs needed to help us change all these, to help us make all these state changes in an efficient way. So on the output side here, processing view events is also very, very easy. So if you use a when clause like this, you can be confident that you're going to cover all the possible cases of what's coming in. And for a simple model, like I said, triggering intent processing is fairly trivial. We call the process intent functions straight onto the model. Now, that's not something I used to do, but I find that I haven't seen any downsides as I started getting a bit less religious about the intent layer and having a processor that converts the view events into intents. Like simply passing those in like that and having the model create its intent works pretty nicely. All right, so JS, the JS section of this talk is a bit light, I have to admit, but the core concepts are here. So with Kotlin JS, Kotlin XML here, Kotlin X HTML has been my library of choice for building views. Another very popular approach is to use React, not native, but React libraries, React.js libraries as a view system. But for me, I found that using Bootstrap was quite enough to generate my own UIs. So with Kotlin X HTML, what you get is a nice DSL that allows you to effectively define your DOM and have handles to whatever pieces of the DOM that you will want to interact with. So we can see here this a bit with the on-click functions in the buttons. And then, it allows you to really target and put your handlers wherever you want. Now, if we move on to a more of a top-level thing here, the main div is made public here, so that the top-level JavaScript will be able to add it straight into the DOM. And then when the attach function of our little view component is going to be called, what we do is we start collecting habit states from the model, very similar to what Compose is doing effectively. Every time the state changes, we refresh the DOM subcomponents directly. Now the difference with Compose, perhaps obviously, perhaps not, is that this, you have to write your own efficient logic. Like if you're not very efficient in the way you redraw your views, you can definitely be very spammy and redraw the whole screen every time, and that's not optimal. Now, you might be wondering, why didn't he use Compose for the web? And I really wish I could. I've tried it a few times, and it tends to, how to put it, it's very beta, so that's obviously going to change, and perhaps it even is much better as we speak. Like every month brings new things. But in my experience, whenever I used Compose on the web with Kotlin JS, it tends to start popping up random compilation errors for very simple things like assigning variables, and like very common programming patterns become verboten, and you can't necessarily access and do these things. But that's probably going to change in the coming months, so that's worth noting down. Event handling on JS is nothing special compared to iOS or Android. So basically, by having your DOM event handlers emit events into a private shared flow, you can then redirect those by collecting that flow during your attach process. And you might be wondering what the view component class looks like. Well, as you can see, it's not doing that much. And quite honestly, I'm not usually a fan of abstract classes, and there's probably ways to even be more efficient with Kotlin JS than this. But this was a simple approach that worked well, and also it sort of sidestepped a few issues from the fact that you're working with single-threaded code in JS that can sometimes be a bit of a pain. So this simple approach really worked well for me. Everybody's got the same ring on their phone. I thought it was mine. All right, so moving on to iOS and Swift UI. I see we're getting short on time, so I'll try to fly by. Swift UI is similar to Compose. It's what I'd call a declarative view system. And thanks to a preview system, we can really quickly see the impact of changes done to the code, so that's really nice. Similar to Compose, you're going to get a system to manage the view's internals, state, and property. So if you remember that edit mode I was flipping around, Swift UI has a similar concept where the view has its own embedded state that doesn't expose to anywhere else. So you can use that to sort of internally flip a few things around. Based on the data the view consumes, it can rebuild itself dynamically. And so effectively, you have something very close to Compose. Even if perhaps, and I don't want to insult anybody that does iOS development as a full-time day job here, slightly less, say, powerful than Compose. Compose has this concept, right, of rebuilding the right portions of the tree. And I find, and that might be my lack of experience speaking here, that with Swift UI, you're a bit responsible for that. I haven't run into situations where it's a big problem, but it's worth keeping that in mind. All right, so before going further, the next few slides I'm going to show, that iOS approach I'm showing here today is in most, and if not in wholly borrowed from the CampKit project, which you've probably heard about if you've at this conference. The very nice folks at TouchLab have open sourced this for the community, and I think they're fairly well known, especially in New York. So if you're starting your own mobile multi-platform project, I really highly recommend you first check out the CampKit. It's really good for most of the big concepts. So how do we consume Kotlin flows from the Swift UI framework? I'm going to be going a bit quick because I think the break is at 10:30, but effectively you first need to create an adapter layer on the top of flows. So that allows you to expose properly typed flows to Swift as simple callback-based subscriptions. These adapters will allow Swift code to cancel subscriptions as needed. Then you can use flow adapters to expose your habit model output to Swift. And we can still expose habit model itself, since the intent processing functions that I showed you earlier can be directly called from Swift code. So that's one of the nice side effects of that approach. Once you have the adapted model, you can create an observable object right there. So this is almost the flow or the shared state flow equivalent for Swift. It's part of the iOS Combine framework. This is Swift's official pub/sub framework. So you can get an instance of the habit model from your DI system, wrap it in an adapter, and then when your observable object activates or deactivates, you can collect or cancel the flow as needed. So these two functions right here, activate and deactivate. Typically, I take the time to shim the process function calls here to avoid exposing the Kotlin model to the rest of the Swift code. Now, once you have your observable object ready, all that's left is to hook them up to the view as so. So when the view appears and disappears, the observables are activated or deactivated as needed. Then we access the habit map straight from inside the view. So similar in a way to how Jetpack Compose code works, it's going to cause the view to rebuild itself and the model state as the model state changes. All that's left is to hook up the button click listeners, and here you have a working UI equivalent to what we've seen on JS and on Android. All right, we're almost done. So the glue that holds everything together, though, is Coin DI, so I want to talk a little bit about that. In the multi-platform space, Coin or Codeine are your main DI choices. You won't really get a chance to use Dagger. So I picked Coin personally mostly because I found it easy to use. We're really only taking a quick look how it works here on Android and iOS. So here you have Coin's basic DSL configuration, which involves adding dependency mappings and modules. Then you need to build, you need the dependency lazies by calling by inject here. So when needed, it's going to cause the auth model instance to be built in this example. And then we do need to start Coin in the right step of the lifecycle on create. So it's very similar to what you've probably used to with Dagger. Here I show the module initialization happening from within application itself, but typically that code could live in the common layer just with a few adjustments. So that's something you're also going to see in the CamKit example. They have like a much more sophisticated Coin example that I encourage you to go look at. For Swift, the way things work, most of the module code I find tends to end up on the Kotlin comment side of things. But it's quite possible if you need to trigger Swift configured initialization code. So by having the Coin vars here, right here, we can have Swift code get dependencies on its own as well. That's something I showed you earlier when we got the habit model from DI while we created the adapted habit model. All right, last point. Need to start to call the Coin starter functions from the right place in your Swift app lifecycle. A bit quick, but you get the general idea. All right, so tracks to explore for your own projects. I've touched on Compose, and Compose obviously, as I said, also works on web, on desktop, and so on. So that's like a really nice thing that you could look into. Firebase, quite interesting with MVI, so I encourage you to look at that. There's like really interesting patterns that are easier to use than having to build your own Ktor callbacks. And yeah, that's about that. Other tracks to explore, more formal MVI stacks, worth mentioning them. So MVI Kotlin and Orbit MVI. So I don't see any phones out, but that's probably going to be in the recording if you're curious to find out where they are. I see somebody taking it. I'll let you take a quick shot. All right. Those are pretty good because they're very prescriptive. At the same time, in my school of thought, sometimes prescriptive is a bit heavy for smaller projects. All right. So we looked at the MVI core concepts. Hopefully, you'll find that those core concepts apply to all the other architecture alphabet soup that you find out there. So MVP, MVVM, MVU, etc. A lot of the concepts that we looked at today apply probably in your own projects, even if you do not have an MVI stack. And we looked at the various implementations of the big three. So this is where I'm hoping that you will go see the source code backing this talk. This is also part of an effort I'm doing with the DroidCon learning platform. This is a lot of the course material I'm preparing for them will be based off of this specific repo. I'm not doing, as of yet, a multi-platform course for them, but it's a good place to reach out if you want to talk about a few of the implementation details or want to see what I'll be doing with this project next. Come and visit, and the discussion board in there will be open soon. And with that, thank you. That's it for me.